Swayam Prabha. Digital India. Educated India.
Next, we will continue the affine spaces. So far we discussed affine transformation, mapping and so on, how to convert the matrices like that. Now we have to go with associated with the vector space. Therefore, the vector and vector subspace is associated with affine. Therefore, it is called as affine spaces. In the following, we will take a closer look at the spaces that are offset from the origin, that is the spaces that are no longer vector space subspaces. Moreover, we will briefly discuss the properties of mapping between these affine spaces which resemble linear mappings. Now, we have a note in the machine learning literature. The distinction between the linear and affine is sometimes not clear, so that we can find the references to affine spaces or mapping as a linear spaces or linear mapping. Now, we have a function. So, just we saw that mapping and transformation in a normal technique in the polar coordinate. Now, we have to go to the vector space, that is affine function. Affine function is a function based on domain to codomain. With a linear function we have to apply, with a linear function plus a constant is called affine function. Now, a function r power n tuple, you take the domain and maps to the R. So, to the one tuple is affine. If and only if it can be expressed as f of x equal to A transpose x plus b for some n vectors A and a scalar b. So, which is sometimes called offset. For example, you take a function 3 vectors defined as f of x equal to 2 into 3 minus 2x1 plus 1 into 3 into x2 minus x3 is affine, because here b equal to 2.3 and a equal to and the corresponding coefficient of x1, x2, x3 minus 2, 1.3 minus 1. So, this way we can write what this set of vectors corresponding to linear expression in terms of f of x equal to A transpose x plus b and separate constant b associated and all the coordinate represent like that, then it is said to be affine function, and this is called it as the scalar is called it as offset. Now, keep it in mind this that will impose into the picturization of orthogonal transformation, so that it will be directly understand how AI and ML are transforming and working, you can easily understand mathematically. Now, any affine scalar valued function satisfying the following variation on the superposition property, like f of alpha x plus beta y equal to alpha into f of x plus beta into f of y for all n vectors x and y, and the scalars alpha beta that satisfy alpha plus beta equal to 1. For the linear function, superposition holds for any coefficient alpha and beta. For affine function, it holds when the coefficients sum to 1. So, when the argument is an affine combination. So, to see that the restricted superposition property holds for an affine function f of x equal to A transpose x plus b, we note that for any vectors x and y and scalars alpha and beta satisfy the condition of alpha plus beta equal to 1, then f of alpha x plus beta y equal to alpha transpose into A transpose into alpha x plus beta y plus b, which is equal to, you multiply them, A into A transpose x plus beta into A transpose y plus alpha plus beta into b. So, A into A, so alpha I take it common, alpha into A transpose x plus b, and then beta into A transpose y into b, and then you see this part is equal to A alpha into f of x, and this part is alpha beta into f of y. So, it means it can be expressed as a linear combination. So, the mapping is a linear mapping. In the second line we use alpha plus beta equal to 1, that is why we used here alpha plus beta equal to 1 for adjustment. so that we have what a relationship got it. So, this restriction is a superposition property for affine function is useful in showing that a function f is not affine. So, we find the vectors x comma y and the numbers alpha and beta with alpha plus beta equal to 1 and verify that f of alpha x plus beta y equal to alpha into f of x plus beta into f of y. So, this is a linear transformation. This shows that f cannot be affine. So, as an example, we verified above the superposition does not hold for the maximum function with n greater than 1. The coefficient in our counter example are alpha equal to beta equal to 1 by 2 which sum to 1, which allows us to conclude that the maximum function is not affine. So, where it is affine, where it is not affine, we can easily understand with the help of the linear transformation. Now, this corresponding mapping. So, once you can understand this picture, so that you can identify how it works like that. So, figure 1 left the function f is a linear, okay, and the figure 2 the function g is affine. So, because it reflected in a opposite way, that is the meaning of what affine. So, but it is not a linear, therefore, the converse is also true. So, any scalar valued function that satisfies the restricted superposition property is affine, and analog of the formula is f of x equal to f of naught plus x1 into f of x1 f of c1 minus f of naught plus and so on xn into f of c1 or epsilon n minus f of naught, we can do that. So, that which holds when f is an affine and x is any n vector. So, that is seeing in the some more exercise given. So, this formula shows that for an affine function, once we know that n plus 1 numbers, that is f of 0, f of epsilon 1 and so on f of epsilon n, we can predict or reconstruct or evaluate f of x for any n vector x. So, it also shows that how the vector a and a constant b in representation of f of x equal to a alpha a transpose x plus b can be found from the function f such that a I equal to f of epsilon I minus f of naught and b equal to f of 0. So, this is the important things to be noted to set where the function is affine, where the function is not affine can identify. Now, let us go with one example. In some contexts, affine functions are called linear. For example, when x is a scalar, the function f defined as f of x equal to alpha x plus beta is sometimes referred to as a linear function of x, perhaps because its graph is a line. But when beta is not equal to 0, so f of x equal to alpha x. F of x equal to alpha x, then it is a linear, therefore, the line passes through the origin, therefore, the function could not be identified. So, f is not a linear. So, in this talk, what we can identify, the standard mathematical sense of this idea is to be discussed. So, if it is affine function of x and this talk have discussing between the linear and affine functions. So, two examples are shown in the figure 2.1 and 2.2 of the line, and now you can see the picture of figure 2.2, the bridge with white W1, W2 and so on, Wn you take it. Here we demonstrated only 3 whites W1, W2, W3 and 3 location we have to join them, and then these whites cause the bridge to sag in the middle by an amount s. So, this snag is exaggerated in this diagram. So, that is you have to make a note point of the down of these pictures shows that where the sag is there. So, this can be identified with the affine function how it is defined. Now, we have a white corresponding to W1, W2, W3. First you start with the W1 is 0, W1 is 1 and the rest of them is not associated, therefore, put 0. Similarly, second row is 0, 1, 0 third 0, 0, 1, and measured sag for the corresponding W1 is 0.12, and then for second weight is 0.31 and third one is 0.26, and we could not predict it immediately, and next we have to associate it with what corresponding affine ideas, so that the answer will come 0.5, 1.1, 1.3, and corresponding measure you have to what to do that it will be 0.481, and that predict is 0.470. So, same way you have to do successive ideas, you have to do the transform, second align will come. So, loading on the bridge of the first 3 column, the associated measured sag at the certain point of the 4th column, and the predicted sag using the linear model constructed from the first 3 experiment, that is the 5th column will represent. So, this table shows that the result of these experiment might look like, with each row representing an experiment and placing the loads and measuring the sag. In the last 2 rows we compare the measured sag and predicted sag using the linear function with the coefficient found in the first 3 experiments. Now, we are going to discuss the affine subspaces. Already we come across what is the meaning of vector space, vector subspace, and the same way we can apply for affine subspaces. Affine space we understood, now we have to go with the affine subspaces. Now, we have a definition, let V be a vector space, x naught belongs to V and U is a subset of V as subspace, then the subset L equal to x naught plus U, where x naught plus U such that U in U and V in V such that there exists U in V, and V equal to x naught plus U is a subset of V. So, this is the definition of subspace, is called affine subspace or linear manifold of V. So, U is called direction or direction space and x naught is called the support point. Now, we can refer this subspace as a hyperplane. Now, affine subspaces are often described by parameters. Consider k dimensional affine space L equal to x naught plus U of V. If B naught, B1, Bk is an ordered basis of U, then every element x in L can be uniquely described as x equal to x naught plus lambda 1 B1 and so on lambda k Bk, where lambda 1, lambda 2 and so on lambda k are in R. This representation is called it as parametric equation of L, and the B1, B2 are the directional vectors and lambda 1, lambda 2 and so on lambda k are parameters. So, it seems to be it is a linear combination of one vector to the another, and then this can be represented as a affine subspaces like that. Now, we have a example, one dimensional affine subspace are called a line and can be written as y equal to x naught plus lambda B1, where lambda in R scalar and U equal to span of B1 in R power n is a one dimensional subspace of R power n. So, this means that the line is defined by support point x naught and a vector B1 that define the direction of the figure 2.13. So, it represent, so B1 is a corresponding one vector, x naught is a corresponding, and combined together I have a vector y. So, this joined together we have a L equal to x naught plus lambda into B1. So, this call it as line or affine subspaces, vectors y on the line x naught plus lambda B1 lie in an affine subspace L with the support point of x naught and direction of Bn. So, the two dimensional affine subspaces of R power n called planes. So, the parametric equation for a plane is y equal to x naught plus lambda 1 B1 plus lambda 2 B2, where lambda 1, lambda 2 are belongs to real number and U is the span of B1, B2 which is subset of R power n. This means that the plane is defined by a support point x naught and two linearly independent vectors B1, B2 that span the direction space. In R power n, the n minus 1 dimensional affine subspaces are called hyperplanes and the corresponding parametric equation is y equal to x naught plus summation I equal to 1 to n minus 1 lambda I b I, where b1 to bn minus 1 form a basis for of an n minus 1 dimensional subspace of u of r power n. This means that hyperplane is defined by support point x naught and n minus 1 linearly independent vectors b1 to bn minus 1 that span the direction space. In R square, a line is also hyperplane. In R cube, a plane is also hyperplane. So, these are all the two important points to be noted, and then in future we have to represent in terms of what line to the hyperplane, plane to the hyperplane, how to do that. So, we have a note in homogeneous system of linear equations and affine subspaces, for A belongs to m cross n tuples of R and x belongs to m tuple of R, the solution of a system of linear equation A lambda equal to x is either empty set or an affine subspaces of R power n of dimension n minus R k of A. In particular, the solution of the linear equation lambda 1 b 1 and so on lambda n b n equal to x, where lambda 1 to lambda n is not equal to 0 0 is a hyperplane in R power n. So, in R power n, every k dimensional affine subspace is the solution of inhomogeneous system of linear equation A x equal to b, where A is in R of m cross n tuple and b in R power m tuple. Therefore, rank of A equal to n minus k. So, recall that for the homogeneous equation system A x equal to 0, the solution was a vector subspace, which we can also think of as a special affine space with support point x naught equal to 0. Now, we have an definition affine mapping. So, for two vector spaces V and W, a linear mapping phi such that V to W and A belongs to W, the mapping phi such that V to W and x map to A plus phi of x is an affine mapping from V to W. So, the vector A is called the translation vector of phi. So, every affine mapping phi such that V to W is also the composition of a linear mapping phi such that V to W and a translation tau such that V to W in W such that phi is equal to composition mapping tau over phi, right. The mapping phi and tau are uniquely determined. So, the composition of phi dash of phi of affine mapping where phi maps from V to W, phi dash map from W to X is called affine. Then the phi is a bijective means both injective and surjective. Affine mapping keeps the geometric structure invariant. So, they also preserve the dimension and parallelism. So, these things are most important for affine mapping.